Hello everyone, welcome to a new short lecture. Again, I'm Edra, your lecturer for this session. We'll do first a topic review. Last meeting on trusses, we actually summarized the step-by-step procedure of truss analysis using method of joints. We also discussed how to look for zero force members in trusses. So you might still be asking, when do we use the method of joints and when do we use the method of sections? We use the method of joints when we are designing a new truss. Thus, we want to solve for all members, including support reactions. On the other hand, we use the method of sections when we are retrofitting an existing truss, and we only want to solve for a few members being retrofitted. Thus, it is possible that from the start, we already know the value of other truss members, especially support reactions. Okay, let's get right into analyzing a sample truss. The dimensions of the truss are indicated as shown. We are going to use the method of sections to determine the internal axial forces in three members FE, FC, and BC. We also have to indicate whether they act in compression or tension. The first step is to actually complete the free body diagram of the whole truss. At point A, we have a pin support. Thus, we have two reactions. We have a vertical reaction and a horizontal reaction. At point D, we have a roller support. Thus, we only have one reaction, a vertical reaction. All directions of reactions are assumed or arbitrary, so it's not really important at this point if you've assumed a correct direction for the reactions. What is important is that you have correctly identified the number of reactions at each support. The third step is to compute for your reactions. Remember, in method of sections, it is assumed that you already know the values of other truss members, especially support reactions, since you are just retrofitting or adding into an existing truss. So it's alright if you compute for your reactions first. I have assumed that all forces going to the right and all forces going up are positive. Also, clockwise rotations are assumed to be positive. We will now be applying the equations of static equilibrium on the whole truss. We will start first by taking the vector sum of all horizontal applied loads and reactions, then equate them to zero. So the load, positive 400 newtons, plus the reaction, negative a sub x is equal to 0. Transposing a sub x to the other side of the equation, we find that a sub x is equal to positive 400 newtons. It's positive, meaning the direction we have assumed in our FBD is correct. So its direction is going to the left as in the original free body diagram. Next, we will take the vector sum of all forces that will produce a moment about point A. Then equate them to 0. Doing this will eliminate the unknown reactions at point A. So, we have the positive moment from 1200 newtons times a distance of 8 meters from point A, plus the positive moment from 400 newtons times its distance of 3 meters from point A, plus the negative moment from d sub y times its distance of 12 meters from point A. Equate everything to 0. So we're going to proceed with simplifying the whole equation. Until we come up with d sub y being equal to positive 900 newtons. It's positive, meaning the direction we have assumed in our original free body diagram is correct. So its direction is going upwards. Finally, we will take the vector sum of all vertical applied loads and reactions, then equate them to 0. So the reaction we have computed a while ago, positive 900 newtons plus positive a sub y plus the load negative 1200 newtons is equal to 0. Simplifying the equation further, we will get positive a sub y plus negative 300 newtons equals 0. Transposing 300 newtons to the other side of the equation, we find that a sub y is equal to positive 300 newtons. It's positive, meaning the direction we have assumed in our free body diagram is correct, so its direction is going upwards. The fourth step is to decide where you will cut your truss. Try to choose a cutting line that goes through all the members that are to be determined. So here in this truss, the best cutting line is shown by section AA because it passes through all three members FE, FC, and BC that have to be determined. Step number 5 is to isolate a section part of the truss. We want to use the side of the truss that involves fewer forces, so in this case, we chose the left side. I also want to reflect the reactions we have computed earlier so that we will have a complete free body diagram of this section truss. You will also see here that I have reflected FE, FC, and BC. My assumption is that these web members are all acting in tension. So seen here, they are acting away from the joints. It's very important to establish this assumption first before we proceed to applying the equations of static equilibrium in our section truss. So for the equations of static equilibrium, I have assumed that forces going to the right and upwards are positive. Also, clockwise moments are assumed to be positive. Step number 6 is to analyze the section truss using the equations of static equilibrium. First, we will take the vector sum of all forces that will produce a moment about point F, then equate them to 0. Doing this will eliminate the unknown forces FC and FE, and it will yield a direct solution for member BC. So, first we have the positive moment from 400 newtons times its distance of 3 meters from point F, plus the positive moment from 300 newtons times its distance of 4 meters from point F, plus the negative moment from BC times its distance of 3 meters from point F, then equate everything to 0. So we're going to proceed with simplifying the whole equation. Until we come up with BC being equal to positive 800 newtons. So it's positive, meaning that the assumption that it is acting in tension in our original free body diagram is correct. Next, we will take the vector sum of all forces that will produce a moment about point C, then equate everything to 0. Doing this will eliminate the unknown forces FC and BC, and it will yield a direct solution for FE. So we have the positive moment from FE times its distance of 3 meters from point C, plus the positive moment from 300 newtons times its distance of 8 meters from point C. Equate everything to 0. So again, we're going to proceed with simplifying this whole equation. Until we come up with FE being equal to negative 800 newtons. It's negative, meaning our initial assumption that it is acting in tension in our free body diagram is not correct, and that actually it is acting in compression. Finally, we will take the vector sum of all the vertical forces, then equate them to 0. Take note that we have a right triangle with a 3-4-5 ratio. So we can use ratio and proportion to get the vertical component of FC. So moving forward, the reaction that we have computed a while ago, positive 300 newtons plus negative 3/5 FC equals 0. So we're going to simplify this equation further. Until we get FC is equal to positive 500 newtons. It's positive, meaning our assumption in our free body diagram is correct. Its direction is acting in tension. So notice that if two unknowns are parallel, like FE and BC, you can take the sum of forces perpendicular to that direction of unknowns so that you can determine directly the third unknown force, which was FC. That is just what we did. So that's tip number 3 for you. The last step is to redraw the free body diagram of your section truss. You have to reflect the correct directions of forces you have just computed. So here you can see that we have corrected the action of member FE. Now it is shown that it is acting in compression. So guys, you can practice at home, you can compute for the same members, but this time you have to use the right side of the section truss. Of course, you should get the same answers. So some of you might be thinking that method of sections is easier compared to method of joints. It actually is. It is more practical and easier to use, especially when you need quick solutions for just a few members. To summarize, let's review the step-by-step analysis using method of sections. First, complete the FBD of the whole truss. Second, compute for the truss reactions using the equations of static equilibrium. Third, decide where to cut your truss. Make sure the section line passes through your unknown forces. Fourth, isolate the truss that has fewer forces. 5. Make assumptions about the action of web members. Are they all in tension or are they all in compression? Step number 6. Compute for member forces of the section truss using equations of static equilibrium. And finally, you have to redraw the FBD of the section truss and reflect the computed values of the members and their correct directions. Thank you so much guys for watching the video. That completes this lecture. Please look forward to additional links about method of sections and additional problem illustrations. Hopefully I can allocate time for that. Again, if this video was helpful to you, I would really appreciate it if you can give it a thumbs up.